If an intelligence wished to speak across the stars, what form would its voice take? Not fragile radio waves fading into cosmic noise, but something enduring, tangible, inevitable, and bound to reach its destination. It would need to survive billions of years, drifting through the thin chaos between suns. It would need to endure heat, cold, and radiation without revealing itself too soon. And when at last it neared another young civilization, it would have to appear natural, unremarkable, a thing overlooked by all but the curious. On July 1st, 2025, astronomers detected something unusual. A faint, fast-moving object, no larger than a small mountain, inbound on a path unbound by the sun. Within days, it was confirmed as 3Y Atlas, only the third known interstellar visitor ever observed passing through our solar system. It moves at over 130,000 miles per hour, its trajectory hyperbolic and fleeting, ensuring that it will brush past the sun, shed a delicate veil of vapor, and then vanish forever into the dark between stars. At first glance, it seemed like a comet, a frozen fragment of ice and stone cast loose from some distant system. But almost immediately, the details resisted easy explanation. Its chemistry is unusual, a coma unusually rich in carbon dioxide, with an extreme CO2 to water ratio of nearly 8:1, among the highest ever measured. Its volatile blend, carbon monoxide, cyanide, carbonyl sulfide, nickel, is oddly specific, almost engineered. Even its speed and trajectory strain our models. And this is not an isolated case. In 2017 came Oumuamua, accelerating unexpectedly as though pushed by an unseen hand. In 2019, 2I/Borisov, carrying the signature of another alien nursery. Now, less than a decade later, 3I/Atlas appears, arriving precisely where our instruments can see it, just as our capabilities have matured enough to notice. Coincidence? Maybe. But 3 interstellar objects in less than 10 years, after billions of years of silence, pushes the odds toward the improbable. Why now? Why this chemistry? Why this trajectory? Its composition deepens the mystery. Observations by the James Webb Space Telescope reveal a coma unusually rich in carbon dioxide, with a CO2 to water ratio nearly 8:1, among the highest ever recorded. Why would an object from another system carry such an atypical chemical signature? Why this particular blend of volatiles, carbon monoxide, nickel, cyanide, carbonyl sulfide, balanced so precisely? Is this simply the fingerprint of an unfamiliar birthplace? Or could it serve some hidden function? If one wished to design a messenger that looked like a natural comet, could such chemistry be part of the disguise? We don't know the answers, but we can ask a better question. If someone somewhere wanted to send something across the stars, something small, patient, and able to masquerade as nature, what would it look like? How would it move? How would it hide? Perhaps 3I/Atlas is only a rock, no different from countless others flung loose by distant worlds. But if it isn't, its design is buried in its speed, its orbit, its materials, and its timing. To understand the object, we must follow the evidence backward, reconstructing the journey of a messenger that may have been traveling toward us since before we learned to walk upright. This is not a conclusion, but an invitation to follow the evidence, question the assumptions, and seek the meaning hidden in the object's motion, materials, and timing. Before 3I Atlas could ever wander the interstellar dark, it first had to escape its cradle. In its home system, immense planets circled like sentinels, their gravity wells deep enough to trap all but the most deliberate travelers. To leave without fuel, to cross billions of miles without firing a single engine, it would need to borrow energy from the giants themselves. This is the foundation of the escape ladder, a sequence of precisely staged planetary encounters where gravity, timing, and geometry conspire to fling a messenger into the void. The principle is simple in form, but exacting in execution. Approach a massive world on the correct vector, pass just behind its orbital motion, and its gravity bends the messenger's path like a lens, stealing a fragment of the planet's momentum and adding it to its own. With each encounter, the object gains speed, without expending reaction mass, trading nothing but precision for energy. But this precision is unforgiving. A targeting error of mere tens of kilometers during a flyby can turn an interstellar journey into a planetary collision, or a silent fall back into the home star's depths. In its earliest stages, the messenger uses this ladder to spiral inward, aiming for a deeper dive toward its sun. Each step stacks upon the last. An outer giant assist redirects its orbit inward. The closer pass increases velocity, allowing the next encounter to penetrate even deeper, and so the sequence cascades. By design, the object prepares itself for the Oberth maneuver, where a plunge near the star transforms modest planetary gains into staggering acceleration. Here, speed compounds speed, and every fraction of energy captured becomes magnified by proximity to the star's blazing gravity well. Three conditions must hold if the design is intentional. First, the reconstructed trajectory must remain fully consistent with the timing and geometry of specific planetary encounters, as though the object had followed a precise choreography rather than a chaotic drift. Second, its energy budget must close neatly. The observed velocity must match what pure gravitational slingshots would yield, requiring no hidden thrust. Third, any deviations in motion would have to appear only during these close passes, confined to windows where gravity, not engines, shapes the path. If all three align, the object's escape is indistinguishable from nature, its true intent hidden behind perfect physics. This ladder of worlds builds not just speed, but subtlety. By chaining gravity assists, the messenger achieves delta-V magnitudes no chemical rocket could sustain while carrying no onboard fuel. Its entire departure becomes encoded in celestial mechanics, timed alignments, resonant loops, and carefully chosen periapses, all setting up the interstellar trajectory we observe today. What we see from Earth is only the consequence, a hyperbolic path at around 130,000 miles per hour, arriving on schedule after eons of silent flight. What we cannot yet see is the deliberate architecture behind it, a motion written into the geometry of planets long before the messenger left its home star. Having climbed the escape ladder of their home system, the architects had not yet given their messenger its true speed. The planetary slingshots brought it inward, setting up the precise geometry for the next maneuver. Now, 3I Atlas dives toward its parent star, not to slow, but to harvest light itself. Here, at the threshold of destruction, photons become fuel, and the messenger becomes a sail. The design reveals itself in subtle choices. The object's surface, dusty, thin, yet highly reflective, creates an unusually high area-to-mass ratio. As the stellar flux intensifies near periapsis, photons streaming outward from the star impart a measurable push, their collective pressure acting like invisible wind on an invisible sail. By altering its orientation relative to the star, the messenger modulates its effective cross-section, controlling both the magnitude and direction of acceleration. This flux cranking allows it to tune its outbound path with astonishing precision. No thrusters, no propellant, only light and geometry. At this distance, timing is everything. The architects exploit the Oberth effect, where the same small impulse at extreme velocity yields an outsized gain. A mere 1 meter per second of effective thrust near periapsis, aligned perfectly with the motion vector, translates into tens of meters per second of added escape velocity. Photon pressure scales exactly with 1/r squared, and at the star's inner boundary, the flux reaches levels billions of times stronger than in interstellar dark. The ladder of worlds from stage 1 built the speed. The star-skimming dive multiplies it. 3 signatures betray the design. First, the messenger's acceleration must track perfectly with stellar distance, falling off exactly as radiation diminishes, a pattern impossible to mimic with random cometary jets. Second, its surface reflectivity must exceed expectation for a body of its size, hinting at a deliberate morphology optimized for photon harvesting. Third, the absence of correlated outgassing, no plumes, no violent jets, reveals control without chaos. The architects needed their messenger to remain comet-like, and yet under the quiet governance of light, it behaves as though guided. By the time 3I Atlas exits this first dive, it carries a new kind of momentum, one drawn from the star itself, layered atop the gravitational energy gained from its planetary dance. Its path is hotter, faster, sharper, aligned for the next resonance in its departure sequence. The architects have taken a silent, unpowered fragment of rock and ice and given it an acceleration profile indistinguishable from nature's randomness, yet optimized for intent. What looks from afar like a simple comet is already performing one of the most elegant pieces of orbital engineering ever conceived. With its outbound velocity amplified by photon pressure and star-skimming acceleration, the messenger turns to its next challenge: geometry. Speed alone is not enough. Without precise control of its orbital plane, the carefully staged flybys ahead would dissolve into chance. To continue chaining planetary assists, the architects bias 3I Atlas toward the ecliptic, the narrow disk where most planets, spacecraft, and future opportunities reside. By holding to a low-inclination path within just a few degrees of this plane, the messenger positions itself in the solar system's natural traffic lane. The engineering is subtle, almost invisible. Minute adjustments made with photon pressure, hypervolatile venting, or field-based steering allow the messenger to counteract the inclination drift caused by gravitational encounters. These trims are executed early, when the leverage is greatest. Small periapsis changes cascade into significant long-term alignment corrections. By shaping its line of nodes before deep space perturbations can scatter it, 3I Atlas locks itself into a corridor where the geometry of future encounters remains stable for millions of kilometers. Three signatures distinguish design from accident. First, the object's inclination remains unusually low, around 5 degrees or less, despite passing through dynamically chaotic regions, behavior improbable under random scattering. Second, its path resists drift. Where natural objects wander in inclination, this one holds its course. Third, when multiple interstellar visitors are compared, we begin to see a faint clustering of low-inclination arrivals, as though some broader survey geometry is being respected. Statistically, the odds of this pattern arising by chance are vanishingly small. Why does this matter? Because staying in the traffic lane opens doors otherwise closed. A low-inclination trajectory maximizes the likelihood of future planetary assists, increasing both speed and navigational flexibility. It also places the messenger in predictable corridors where technological systems, planetary probes, deep space observatories, even surface-based telescopes are most likely to see it. The architects have chosen visibility, but only to those already watching closely. By the time 3I Atlas completes this stage, it has secured more than speed. It has secured access. Every resonant encounter ahead depends on this disciplined alignment, and the corridor it now occupies shapes the very survey patterns that make its detection possible. What looks from Earth like statistical accident begins to resemble something else: the deliberate threading of a cosmic needle, designed to pass through the lanes where watchers are most likely to be found. Beyond the star-skimming dive, the messenger enters a region where photons yield to plasma, where the stellar wind flows outward, carrying tangled magnetic fields. Here, the architects unlock a different form of control. By carefully shaping the ionization of its coma and surface, 3I Atlas couples to these fields, turning the star's own charged breath into a steering force. This is magnetosailing navigation by plasma-tail interaction, where subtle Lorentz forces act like invisible rudders across millions of kilometers. The mechanism relies on precision at the smallest scales. Charged dust grains and ionized gases are released from the messenger's surface in controlled patterns, giving its extended coma a variable electrical state. In this way, the messenger can tune how strongly it interacts with the interplanetary magnetic field carried by the solar wind. By increasing charge at key moments, it catches more of the field lines, letting them tug at its extended envelope. By reducing it, the coupling weakens, allowing it to slip free. Across weeks or months, these faint forces accumulate into meaningful side trims, bending its outbound vector without firing a single engine. Three signatures would expose this control to careful observers. First, polarization studies of its coma would reveal a non-random charge distribution inconsistent with a natural outgassing pattern. Second, its acceleration spikes would track directly with solar wind variability, rising and falling in sync with flares and coronal mass ejections. Third, its dust tail would show distinct kinematic features, subtle deflections matching the orientation of the magnetic field rather than following the expected gravitational arc. No random comet behaves this way, yet 3I Atlas does so invisibly, riding currents we rarely think to measure. This is the final refinement before escape. By the time the messenger exits its star's Hill sphere, its trajectory has been sharpened to an exquisite tolerance, degrees collapsing to arc minutes, timing locked to within seconds. Magnetic side forces have replaced propellant just as photons replaced thrust, each layer of design cascading into the next. What appears to us as passive adaptation to space weather is, under the architect's intent, a controlled dialogue with the star itself. When 3I Atlas leaves this regime, its outbound geometry is fixed. Every gravitational assist, every planned resonance, every survey opportunity ahead depends on the precision achieved here. The architects have shaped its course without engines, reaction mass, or beacons, only by leaning on the forces already written into the physics of their sun. From this point forward, the messenger no longer belongs to its home system. It is already aimed toward ours. Even with the star-skimming boost, photon sailing trims, and magnetic side force corrections complete, the messenger still faces one final challenge before escaping its birth system entirely: the precision of its departure velocity. The architects resolved this through a design of stored tension, turning internal stresses into bursts of controlled acceleration. By exploiting thermal cycling and rotational flexure, 3I Atlas carries within it a reservoir of latent energy, waiting for the right moment to be released. The mechanism is elegant. As the messenger spins, engineered seams within its structure absorb uneven heating from the nearby star, building stress along predetermined fault lines. When these seams rupture, they expose pockets of volatile, rich material, releasing sudden jets of gas and dust. Properly timed, these miniature outbursts produce discrete directional impulses, each imparting a controlled delta V. Where a natural comet vents unpredictably, the messenger's attitude control ensures these ruptures occur exactly when and where they will have the greatest effect. Three lines of evidence would betray the design. First, astronomers would detect brightness spikes, sudden increases in the light curve, synchronous with outburst events, consistent with vented plumes. Second, orbital fits would reveal stepwise accelerations, distinct plateaus of velocity where delta V arrives in discrete packets rather than gradual drifts. Third, the geometry of the emitted dust would show asymmetric fans, tightly aligned with the resulting changes in trajectory. Natural bodies rarely exhibit all three in combination. Here they are signatures of intent disguised as chaos. This technique allows the architects to sharpen their trajectory without consuming onboard fuel, stacking yet another layer onto the departure strategy. Each kick fine-tunes the periapsis angle, optimizing the geometry for the final Oberth exploit and the sequence of remaining planetary assists. With each outburst, the outbound vector grows more exact, folding the residual gravitational binding energy into controlled escape momentum. By the time the last engineered venting completes, 3Y Atlas has reached its locked departure speed. No further steering impulses are needed. The final planetary assist lies ahead, the last turn before the endless straightaway. Beyond this point, the messenger will no longer belong to its star. It will belong to the deep, carrying its intent along a trajectory set with exquisite precision, already aimed toward the distant future and an unsuspecting sky. At the boundary of its home star's dominion, the messenger undergoes its most dramatic transformation. Where earlier maneuvers relied on gravity, photons, and plasma in subtle combination, now the design reveals its true scale. 3I Atlas is not merely an icy fragment, it is a sailcraft. Its thin engineered geometry and extraordinary reflectivity give it an extreme area-to-mass ratio, so much so that the faint push of starlight becomes its primary engine. With slingshots and outburst kicks complete, the messenger unfurls into a precision cone, a light sail calibrated for the silence between stars. The mechanics are unmistakable to those who look closely. As radiation pressure falls off with distance, the messenger's acceleration scales in exact proportion to 1/r², tracking the stellar flux with mathematical fidelity. Its thrust vector responds not to random jets or chaotic outgassing, but to attitude control, tiny adjustments in the sail's orientation relative to the star. Through shifts in reflectivity and controlled warping of its surface, the messenger aligns its trajectory with exquisite precision, as if following a long prescribed attitude law. Three features separate this design from chance. First, its reflectivity and infrared profile exceed what bulk cometary material can explain, suggesting a morphology thinner than any natural fragment. Second, its acceleration vector remains perfectly anti-stellar, pointing away from the light source in smooth, continuous fashion, without the noise of venting or fragmentation. Third, the torques shaping its motion align with sail normals, not with random orientations of dust or ice jets. Every movement echoes the behavior of a controlled sail, rather than a drifting rock. This stage marks the decisive break. The messenger is no longer bound to its origin system. Photon thrust, precisely vectored, carries it across the star's Hill sphere and into the domain of interstellar space. The cone of departure vectors it occupies is narrow by design, a corridor set long before launch and refined through every maneuver to this point. Within that corridor lies the path toward our own star, a trajectory achieved without propellant, without beacon, only through the patient orchestration of celestial forces. When 3I Atlas leaves its system in this way, it ceases to be a wanderer and becomes a navigator. Its cruise velocity is no accident. Its outbound geometry is not chance. From this moment onward, it is a true interstellar messenger, carrying the architect's intent locked into the fabric of its light sail, coasting cleanly on a path written for us to one day notice. Now beyond the pull of its home star, 3Y Atlas enters the quiet of interstellar space, but its journey is far from passive. At these scales, even the smallest navigational errors compound across thousands of astronomical units. To maintain the precision set by earlier stages, the architects give their messenger a final layer of control cometry jet vectoring, using stored volatiles as built-in fuel-free microthrusters. The design relies on controlled sublimation of volatile compounds, carbon dioxide, carbon monoxide, and water embedded within its structure. By orienting the messenger so that selected surface regions face starlight, the architects trigger localized jets on demand. These faint plumes produce continuous micron-scale thrust, imperceptible to casual observation, yet sufficient to steer a course measured in fractions of a degree. Through slow, deliberate attitude slews, 3I Atlas matches its thrust vector to its outbound trajectory, quietly correcting deviations accumulated during its high-energy maneuvers. Three signatures distinguish this intent from natural outgassing. First, photometry of active vents would show temporal coherence with the object's subsolar orientation, suggesting sunlight-driven venting is being purposefully modulated rather than randomly triggered. Second, measured non-gravitational accelerations would close cleanly against a momentum budget derived from gas production rates, no missing forces, no unexplained impulses. Third, trajectory deviations would align with modeled jet vectors, forming a consistent match between attitude, heating, and motion. You see, precision here matters more than speed. Across millions of kilometers, even a fraction of a millimeter per second can determine where the messenger passes centuries later. The sublimation system, whether it's engineered vents or cleverly retained surface ices, provides these trims without the need for sails, thrusters, or onboard fuel tanks. The messenger is quiet, self-regulating, and functionally autonomous, with its course being refined continuously without any external intervention. By the time 3I/Atlas completely leaves the fading influence of its star, its outbound vector is exact. Even as the solar flux diminishes and photon pressure fades, the messenger has secured its long baseline accuracy for the deep-time cruise ahead. What might appear as the natural breathing of an interstellar comet is, under the architect's design, a system of precise micro-thrusts that keeps the trajectory true, ensuring that after untold millennia, it will still arrive exactly where it was meant to go. As 3I/Atlas drifts deeper into interstellar space, the photons that once drove its acceleration now weaken, their influence diminishing with distance. Yet, the architects have prepared for this scenario, embedding within the messenger a quieter, slower form of control: thermal biased outgassing. This system exploits engineered surface asymmetries to generate passive, persistent torque and drift corrections without any moving parts or active commands. The principle is simple but, elegant. The messenger's crust is deliberately heterogeneous, one hemisphere sealed under refractory volatile poor material, while the other is layered with volatile rich deposits designed to sublimate when illuminated. This built-in anisotropy turns sunlight, even faint, distant sunlight, into a directional force. By maintaining a specific attitude, 3I/Atlas controls which regions are exposed to heat, allowing volatile sublimation to occur preferentially from warmer patches. The resulting microjets bias, thrust along predictable axes, slowly steering the craft and countering off-plane drift accumulated across billions of kilometers. Three indicators really distinguish this design from natural cometary venting. First, thermal infrared mapping would reveal stable hemispheric temperature contrasts, tightly correlated with known volatile distributions on the surface. Second, the resulting non-gravitational accelerations would remain phase-locked to the messenger's rotational geometry, maintaining a consistent alignment between acceleration vectors and illuminated hotspots. Third, compositional signatures, such as skewed carbon dioxide to water ratios in vent proximal outflows, would persist across multiple cycles, reflecting engineered layering rather than random fracture-driven mixing. This mechanism requires no moving assemblies, no actuators, and honestly, no continuous supervision. The architects exploit passive physics. Light warms one hemisphere, sublimation follows, thrust emerges, gentle, steady, reliable. By maintaining attitude control through deliberate mass distribution and energy management, 3I/Atlas keeps its orientation stable while conserving every fragment of stored volatile mass. By the time the messenger enters truly starless depths, where solar influence dwindles into background noise, its trajectory remains locked and its alignment uncompromised. To an observer, its motion would appear indistinguishable from a natural body lightly sculpted by thermal gradients. But under the architect's design, these gradients are purposeful, tuned for subtle yet continuous control over the messenger's orientation and outbound geometry as it crosses into the long silence between suns. Even with sails, sublimation control, and magnetic steering, the architects planned for uncertainty. Over millennia, even a messenger as meticulously designed as 3I/Atlas might encounter the unexpected: a dense dust field, a rogue gravitational tug, or an unforeseen perturbation from interstellar plasma flows. In these rare contingencies, the architects embedded a final safeguard: recoil-based impulse hopping, a high-gain backup system capable of restoring course authority when all other methods fail. The design leverages a fundamental principle: momentum exchange. At select locations within the messenger's structure lie engineered fragmentation seams or concealed volatile canisters, each prepared to eject material in controlled bursts. When triggered, 3I/Atlas deliberately sacrifices a small fraction of its own mass, producing precise recoil impulses. These kicks, properly timed near specific true anomalies along the orbit, add targeted delta V to correct deviations in speed, inclination, or spin. With only a few uses available, each deployment is carefully reserved for the highest value mid-course recoveries. So there are three key signatures that, would really set this design apart from just random natural fragmentation. First, the light curves would show these sudden, discrete steps that line up with material ejections, rather than the kind of gradual dimming you'd expect from passive erosion. Second, if you look at the orbital fits, you'd spot these instantaneous delta V jumps, velocity corrections that just don't match up with any known gravitational or radiation-driven forces. And third, when you track the dust fragments, their ejection velocities would be aligned with the restored trajectory, which, well, points to a recoil event that's tuned for intent, not just chance. This capability, honestly, it's not meant for routine steering. Think of it more as insurance, a system that's really built for those low-probability but high-impact scenarios where you absolutely have to recover precision or else the mission could fail. So, if an unexpected deflection happens, the messenger can release a small packet of mass, or even fracture a pre-engineered seam, producing controlled thrust without needing stored fuel or any active propulsion systems. By preserving this reserve, the architects make sure that 3Y Atlas keeps authority over its path, even in the most chaotic environments. To distant observers, these sudden accelerations might just look like natural outbursts or, random fragmentation events. But inside the design, they're actually deliberate, planned corrections, used rarely but absolutely essential for maintaining the long arc of a journey that's measured in light years and centuries. As 3I Atlas crosses the threshold into our heliosphere, the nature of its journey shifts. After eons of quiet acceleration and meticulous vector control, the messenger now prepares for a far rarer maneuver, slowing down. At interstellar velocities exceeding 200,000 kilometers per hour, photon sails and micro-thrusts no longer matter. The time to influence speed through subtle forces has passed. Now, the architects rely on gravity, threading a corridor of planetary alignments designed long ago to execute braking maneuvers with exquisite precision. But to reach these encounters at precisely the right geometry, stealth navigation begins. The messenger activates controlled venting systems embedded deep within its structure, turning sublimation into an intentional AI-managed steering method. By carefully sequencing vent duty cycles, 3I Atlas produces thrust vectors that appear indistinguishable from natural cometary activity. To the casual observer, it breathes as comets breathe, shedding gas and dust under solar heating. But beneath this disguise, the venting follows a strict choreography. These microbursts synthesize smooth, continuous corrections, aligning the object perfectly with the periapsis corridor required for downstream gravity-assisted braking. Three signatures hint at this hidden intent. First, the gas ratios of emitted plumes subtly drift in ways inconsistent with passive thermal models, revealing a tuning of volatile layers to match mission timing. Second, the venting sequences display duty cycle modulation, deliberate bursts and rests forming a structured pattern rather than the chaotic irregularity of natural jets. Third, high-precision astrometric fits would expose clean, maneuver-like vector corrections, too stable and phase-locked to arise from random sublimation alone. As the messenger nears the solar system's planetary lanes, crowded with gravitational opportunities and hazards alike, these covert adjustments preserve both precision and concealment. The AI biases orientation subtly, ensuring vents fire at exact rotational phases, always disguising thrust signatures beneath a natural-appearing coma. To outside observers, there is nothing remarkable about the activity, but the vector alignments converge on a pre-computed arrival corridor, so improbably precise it borders on impossible by chance. By the time 3I Atlas completes this phase, it has threaded the narrow entrance to its braking sequence. The geometry is locked, the first planetary pass, the first planned slingshot, and the initial stellar dive at the destination all line up within tolerances measured in kilometers after a journey spanning light years. What to us looks like the chaos of cometary venting is, under the architect's design, the quiet navigation of a machine fluent in disguise. Long before sunlight dominates, 3I Atlas begins preparing for arrival. At speeds still exceeding 200,000 kilometers per hour, the architects cannot rely on photon pressure or passive sublimation to meaningfully influence its trajectory. Slowing down requires foresight, precision, and energy stored since launch. The Messenger carries a reserve of hypervolatile ices, nitrogen, carbon monoxide, oxygen, materials chosen for their ability to sublimate at extremely low temperatures, far beyond the heliocentric distances where ordinary comets remain inert. These volatiles are the architect's first braking tool. At distances of 50 to 200 astronomical units, sunlight is still weak, but targeted venting of hypervolatiles allows the Messenger to generate early, powerful jets. These cold-driven impulses nudge the trajectory long before water ice activity begins, shaping the Messenger's periapsis distance with high efficiency. By deploying these jets in carefully phased sequences, 3I Atlas threads its initial arrival corridor, reserving an exact encounter window for downstream gravitational assists. Three signatures distinguish this technique from natural activity. First, a hypervolatile rich inventory produces gas compositions far outside cometry norms, measurable in ratios of carbon monoxide, carbon dioxide, and nitrogen relative to water. Second, activity begins far too early, with outgassing observed at distances much greater than 3 astronomical units, long before standard sublimation models predict jets. Third, the resulting non-gravitational accelerations scale precisely with hypervolatile production rates, independent of expected thermal-driven profiles, revealing control rather than chaos. With this system, the architects shape their slowdown ladder. Each vented burst is synchronized to place 3I Atlas on an inbound trajectory perfectly tuned for ahead-side planetary assists, gravity slingshots designed to shed speed, not gain it. At the destination, this sets up a chain of resonant dives. Periapsis trims refine geometry, star-skimming accelerations, shift angles, and planned planetary encounters bleed away velocity in a controlled sequence. These operations are staged over multiple cycles, each interaction preparing the next. By the time the Messenger nears the inner system, its corridor is locked. The object transitions from freefall into a captured eccentric orbit, perfectly aligned for a planned rendezvous window. What appears from Earth as premature, chaotic outgassing is in truth a carefully engineered braking strategy, the use of exotic ices stored for millennia to manipulate geometry long before heat takes over. With these early maneuvers complete, 3I Atlas positions itself precisely where it must be for the final approach. Jupiter waits at the crossroads, its gravity stretching deep into interplanetary space, shaping the paths of worlds and wanderers alike. For 3I Atlas, arriving at nearly 200,000 kilometers per hour, this is where speed becomes strategy. The Messenger cannot stop outright. The architects have no reason to fight the sun head-on. Instead, the goal is redirection, a calculated exchange of momentum that pivots the object onto a corridor aligned with Earth's own motion, turning what would have been a fleeting pass into an intersection designed long before we learned to look skyward. The maneuver balances on a knife's edge of timing and geometry. Arrive too high or too low, and Jupiter flings the Messenger outward into deep space forever. Arrive too early or too late, and the energy exchange collapses, wasting the single chance to thread the corridor. But at the right vector, Jupiter's immense gravity provides the architects with a tool more subtle than thrust, more efficient than any sail. It reshapes velocity itself, bending the object's outbound trajectory while preserving its speed relative to the star. Where 200,000 kilometers per hour seems blistering from one frame, from another it becomes alignment. Velocity matched not against distance but against the moving platform of Earth's orbit. 3 clues would betray the deliberation behind this passage. First, the encounter corridor would fall within a vanishingly narrow slice of phase space. Tolerance is measured in kilometers after a journey across light years. Second, the resulting redirection would match too perfectly with the dynamical windows connecting Jupiter's gravity well to Earth's orbital path. Third, and most revealing, the path in and the path out would carry residual accelerations no comet could explain. subtle shaping forces accumulating into a vector bias impossible to attribute to randomness alone. After the pass, 3I/Atlas enters its final arc. The messenger now lined up along an Earth-relative trajectory so improbable it strains coincidence. To us it appears a natural comet wandering into survey range, but the signatures, chemical, dynamical, geometrical, suggest orchestration layered beneath the noise. What happens next is no less uncertain. Does it fall inward for another star dive, setting up a braking loop invisible until too late? Does it aim for a silent rendezvous in the cold shadow of interplanetary space? Or does it simply pass us by? A message meant not to deliver, but to provoke the question itself. We watch, measure, and model, but the deeper purpose remains hidden. If Oumuamua, Borisov, and now 3I/Atlas are steps in a sequence, then we are only beginning to understand the pattern. Are we the audience, the experiment, or simply bystanders to a dialogue older than our species? The path tells a story, but its meaning lies in the timing, and timing, perhaps, is what has been chosen for us. The messenger bends past Jupiter, threading an ancient corridor in space-time, leaving us to wonder when and how the answers will finally arrive. If an intelligence wished to speak across the stars, it would not choose fragility. It would not gamble on radio whispers lost to background noise or signals erased by the churn of time. It would build something enduring, a messenger disguised as nature itself, immune to suspicion until the right eyes were ready to see. Perhaps 3I/Atlas is only ice and stone, a relic of some forgotten system flung aimlessly into the dark. Perhaps. But coincidences are stacking 3 interstellar objects in less than a decade, each arriving on trajectories improbably precise. Their speeds, their chemistries, their timing, all just inside the thresholds of plausibility, as though someone designed them to pass as natural until curiosity sharpened into recognition. If intent hides here, then we are already part of a conversation older than our species. The architects may not speak in words, but in motion, mass, and light. Messages launched millennia ago, riding gravity and photons across gulfs where language fails. And now, at this moment in history, these messengers converge on a single planetary system whose telescopes are finally awake, ours. We do not know whether 3I/Atlas carries information, a test, or merely proof of concept. Perhaps we were never the target, merely the witness meant to notice the timing and wonder why. But there is one truth we cannot escape. Someone, somewhere, set events in motion long before we had names for the stars. As the messenger departs into the void, leaving us only data, models, and questions, we are left with a quiet certainty. We were meant to see this. And if we were meant to see it, then we were also meant to decide what happens next. The sky is no longer silent. It is waiting.